In order to successfully share data between two completely isolated machines, you first have to establish a solid physical link. But plugging in a cable does not mean those machines can actually talk. Without 5 absolute prerequisites in place, that copper wire is useless. First, you need a sender to generate the data and a receiver capable of accepting it. Third is the transmission medium, the physical pathway the data travels across. And fourth is the message itself, the actual bytes of information being shared. The fifth pillar makes the entire system function. You need a protocol. In engineering, a protocol is a rigid, agreed-upon set of rules governing how data is transmitted. If the sender speaks one language and the receiver expects another, the connection is meaningless. Hardware provides the raw capacity to move electrons from point A to point B. It is the logical protocols that actually structure those electrons into intelligible communication. Network engineers evaluate the success of those protocols against 4 strict performance metrics. The first is delivery. The system must route the data to its exact intended destination, ensuring no unauthorized device intercepts it along the way. The second is accuracy. External interference can flip a single 0 to a 1 during transmission. The network must be able to detect and correct these errors so the message arrives perfectly intact. The third is timeliness. Packets of data have to arrive in the correct sequence. If the end of an audio file arrives before the beginning, the playback fails. Looking at this timeline graph of packet delivery, we can define the fourth metric, jitter. Jitter measures the variance in packet arrival times. If packets arrive at wildly uneven gaps, it destroys the viability of real-time feeds like video calls. A system that fails even one of these criteria is broken. Every subsequent decision about wiring, hardware, and software is dictated by the need to satisfy these 4 rules. Once the protocols are established, engineers must define how the data physically traverses the medium. There are 3 modes of directional flow. The first is simplex mode. It acts as a strict one-way street. A device like a keyboard can only send data to the monitor. It can never receive data back. The second is half duplex. Data can move in both directions, but with a hard sequential limitation. Like a military walkie-talkie, only one node can transmit at a time. The channel must be clear before the other node responds. Finally, full duplex mode allows for simultaneous bidirectional transmission. Both devices can send and receive data at the exact same moment. How those devices link up matters just as much as how the data flows. In a point-to-point connection, 2 machines have an exclusive, dedicated physical link. In a multi-point connection, several machines share a single backbone cable. Sharing a single line introduces an immediate physical hazard. If 2 nodes transmit simultaneously over a multi-point link, their signals collide, corrupting the data. The hardware configuration dictates the software required. Because of this collision risk, engineers are forced to build strict access control mechanisms to regulate which machine is allowed to transmit at any given millisecond. The physical geometry used to wire multiple devices together in a local area network is called its topology. In a full mesh topology, every single machine is wired directly to every other machine on the network. There is 0 congestion because every pathway is private. The constraint here is the mathematics of physical space. The formula for calculating the required duplex links is n times n-1 divided by 2. If your network scales up to 50 computers, you suddenly need over 1,200 dedicated cables to connect them all. To reduce that physical sprawl, engineers use a star topology. By placing a central hub or switch in the middle, each computer only needs a single cable connecting it to the center, drastically cutting infrastructure costs. But that efficiency introduces a massive vulnerability. The central hub becomes a single point of failure. If that switch loses power, the entire network drops immediately. Alternatively, a bus topology uses one continuous main cable. Nodes are tapped into this shared backbone using small drop lines, minimizing cable length even further. This design suffers from physical signal degradation. As the electrical impulse travels down the wire, it loses energy as heat, requiring hardware repeaters to boost the signal. And when the signal hits the end of the wire, it reflects backward, requiring physical terminators to stop the echo. There are other configurations, like a ring topology, where packets circulate in a continuous one-way loop. or hybrid layouts that combine multiple topologies together to fit a specific building. There is no flawless design. Building a network architecture requires constantly trading physical robustness against material costs and the math of scaling. Managing all these varying topologies and physical limitations at once is impossible. To maintain order, engineers compartmentalize the communication process into stacked software abstraction layers. The International Organization for Standardization designed the OSI reference model. It divides network functionality into 7 independent layers, starting from the physical cables at layer 1 up to the user-facing applications at layer 7. As data moves down the stack, each layer performs a specific function, wrapping the raw data in its own distinct header of routing information before passing it to the layer below. This process is called encapsulation. While brilliant in theory, the OSI model proved far too rigid and complex to effectively deploy in the real world. Instead, the modern internet runs on the TCP IP model. It consolidates the stack down to 4 layers. The bottom 2 OSI layers merge into a single host-to-network layer, and the top 3 merge into a unified application layer. This strict segregation by layer is the most powerful concept in networking. Because the layers operate independently, you can upgrade a physical fiber optic cable at the bottom without having to rewrite the software of your web browser at the top. By isolating the chaos of hardware into distinct protocols, local area networks gained the flexibility to eventually stitch themselves together into a massive global internet. A layered architecture requires a layered addressing system to ensure encapsulated data finds its target. At the lowest level, the network uses physical addressing, commonly known as a MAC address, operating at the data link layer. A MAC address is permanently imprinted onto the physical network interface card of a computer. It operates strictly within local jurisdiction. It uniquely identifies a single machine inside an office building, but it cannot route traffic across the wider internet. For that, you need logical addressing, handled at the network layer. This is your IP address. IP addresses act as universal identifiers. They give routers the exact geographical coordinates needed to take a packet, jump out of that local circle, and navigate it through an array of entirely separate physical networks. The physical MAC address identifies exactly who the local machine is, while the logical IP address maps exactly where on the globe that machine is located. When a user hits send, their message is chopped into packets, wrapped in IP and MAC headers via encapsulation, pushed down the TCP IP stack, and fired out over a full duplex transmission medium across a physical topology of routers. This exact mechanical sequence executes billions of times every single second, strictly adhering to the performance constraints of absolute accuracy, timeliness, and precise delivery. There is no magic in the network. It is just the ultimate scaling of an isolated sender and a single receiver, a triumph of standard protocols forcing millions of chaotic pieces of hardware to operate as one unified engine.